Today we're going to be talking about inverse functions. An inverse function basically happens when you take the x or the y value and switch them. So here's my example function. I have y equals 2x minus 4. The first step in finding the inverse function for this particular function is to take the x and the y and switch them. So instead of saying y equals 2x minus 4, I say x equals 2. After I've done that, I need to solve for y using the properties of SADMAP. So to isolate y, I'm going to add 4 on both sides, and then I divide everything by 2. Remember that the entire side gets divided or multiplied, so I'll get x over 2 plus 2 is equal to y. These functions are inverses of each other. Inverse functions are mirrored over the line y equals x, so they're reflected over a particular line. So let's look at my Desmos example here. So my original function is y equals 2x minus 4. If I graph the inverse function, if I were to show you the line of y equals x, so just the line with a slope of 1, I see that the inverse functions have been reflected over this particular green line. It's the same way for all inverse functions. So here's another example. So my original function is y equals x squared. If I take the inverse, I'm obligated to switch my x and y values. So now I have x equals y squared, and then I solve on both sides to solve for x. And then I solve on both sides for y. So before I even begin to simplify this, let's just graph the original equation. So we know that the graph of the original is a parabola. Let's say that we're going to make a chart x and y, and I were to plug in y equals 1, well then x is 1, y is 2, x is 4. I would then build a parabola that was turned on its side like this, or like I showed you before, reflected over this invisible line y equals x. So notice I haven't solved and isolated y by itself yet. The vertical line test is used to check original functions to make sure that they are a function. The vertical line test says, if I draw a vertical line at any point through the function, will it ever pass through more than one point? And if the answer is no, it only passes through one point at any given part of the function, then yes, this is an actual function. I also see that the vertical line test does not work on the inverse function. So if I isolate for y and get y by itself, solving for the inverse, I see that this here is not actually a real function. If I were to draw a line through it, it crosses twice, meaning that the inverse is not actually a function. However, if we limit the range of an inverse function, so remembering that the range means how far a graph goes up or down. For example, the range of this function, y equals x squared, is simply y is greater than 0, because there are no values of the graph that go below the value of y equals 0. Well, if we limit the range of the inverse, and let's say that we now decide to say, well, the range must be y is greater than or equal to 0, we've then just cut off all these other values down here, because y cannot go below the value of 0. And if we cut off those values, now the inverse passes the function test, and it is now a function. So by limiting the range, and usually we note this by putting comma and then the range here, we can convert the inverse of any function to be actually a function as well, even if originally it was not. So just recapping here, originally the inverse was a parabola reflected over this line, and it was not a function because the vertical line test didn't work. This part here was still here. We still included that in our inverse. So as soon as we limited the range of the inverse function by saying that y has to be greater than 0, no part of the function where y is less than 0 is included, we've chopped off this part and we've now converted this into a function because the vertical line test now works. Here's an example of the type of problem you might encounter. You're supposed to find the inverse function of y equals x squared plus 3, where y is greater than 0. So again, our first step is just to switch out the y and the x's. So we're going to have x equals y squared plus 3, and now we need to isolate to get y by itself. So we can just use SADMAP, and we'll get the square root of x minus 3 equals y. We also see that we've been given a range here. So when we graph this, using our knowledge of radical functions, I see that because this number is inside the radical and it's negative, it's been moved to the right 3. My function, roughly sketched, will look like this. Again, I don't draw this bottom part here to show the negative or unreal solutions, because I've been given a range that says, well, y has to be greater than or equal to 0. So this part here, I just entirely do not include. So here's the inverse function, and here is the graph of the inverse function. So here's a little secret about inverse notation. Another way of writing this would be to say f of x is equal to x squared plus 3. When we write the inverse function, what you're going to see later in math is inverse function notation is always written like this. When I want to say the inverse of the original function, I say f to the minus 1 of x is equal to. So this represents the inverse of whatever original function you were given. I can then rewrite it as f to the negative 1 of x is equal to square root of x minus 3. Okay, this gets a little bit trickier when we go backwards. So we've already talked about how domain and range kind of affect each other. Here we have a problem that has f of x equals square root of x plus 2, and you're asked to find the inverse. This problem doesn't actually tell you, but you should know by now that a graph of a square root is going to look like this. So what this problem doesn't tell you is that, well, secretly, even though you know that the graph of a radical looks like this, it's actually half of a parabola, where we don't include the unreal solutions, because we don't want to bother with taking the square root of a negative number that can't be graphed. So the range of this function is secretly y is greater than or equal to 0. Now, we know this because we see that this graph has not been moved up, it has not been moved down, there's nothing affecting it except that we know that it goes left too. So you're going to have to use your knowledge of how radical functions are graphed to figure out what the range of this function is. This is going to become important because when we find the inverse, the range is going to affect the domain of our inverse function. Let me show you how that works. So I'm going to store my range over here so I don't forget it. I suggest that you also do this in your homework so you don't forget as well. Let's go ahead and trade our input and our output. So once you've gone ahead and written it in function notation, the inverse is equal to x squared minus 2, you might think, I'm done. However, you're not. There's an imaginary set of numbers that's not included with every single time we have a radical function like this. So when I see this and I find the inverse, I take this range and I simply change the y to become an x. And that's all I do. All I do is take this y here from my original range and I switch it out and I say, okay, well x is now greater than 0 instead of y. Why do we do that? Let me regraph my original function. I know that my original function is a radical that it seems like it's been moved left to, and it goes like that. If I were to reflect that over an invisible line, y equals x, just like we've been doing for all the other equations, I don't have another half to this. This is not a parabola. But the inverse function is a parabola. Now, it doesn't make sense for the inverse of something that isn't a parabola to have an inverse that is. So when we do our inverse function, I'm going to draw it here in blue, it's going to be moved down 2, and it's only going to have one side. So you can see now how it's been reflected over this line. Now, if I had graphed it just like I would graph a normal parabola, it would have another side. But that doesn't make any sense, because if this one doesn't have another side, the inverse function definitely could not have another side either. So that's why we chop it off right here at this cutoff point, where you can see that it's been evenly reflected over this line y equals x. So let's just go back and review what I did. I recognize that it's a radical function, which means that it has a secret range that we need to find. So I look at it, I look at the transformations, and I see that it has not been moved up or down, so the range is just normal. Y is greater than or equal to 0. I go ahead and I solve for my inverse function, and then all I do is I take that range and I switch the y to become an x. Then when I graph it, I can see that this original function is perfectly reflected in the inverse.